Okay, so another example of the same type. Once again, case 2, this is the stuff that you're going to see in the formula sheet. So it will mention clearly, you have a single lambda, single eigenvector. Next step immediately is to find a generalized eigenvector called U from a same system that gave you the eigenvector. It's as simple as that, right? You set up the same system, but the right-hand side is zero, is the V bar, is the eigenvector you just found, not 0, 0. And then you solve for another eigenvector. And then your solution, of course, will look like that. I mean, the second independent solution will be a linear term here times e to the lambda t. So let's proceed with the eigenvalues and vectors first. So again, very carefully write the trace. Minus 3 minus 1, that's minus 4. So lambda square minus the trace times lambda plus the determinant, lots of negative signs. Make sure to do it correctly. So minus 3 times minus 1 minus negative 1 times 1 equals 0. So my characteristic equation will be lambda squared plus 4 lambda, and this is plus 3 plus 1. And if we solve, we get lambda equals minus 2, a single eigenvalue. And the eigenvector, subtract minus 2 from the main diagonal, and then minus 1, minus negative 2. So we're solving for V bar now, for the eigenvector. And we get minus 3 plus 2, that's minus 1 and 1. Minus 1 plus 3 is 1. Pause for a moment, because at this point, if you stare at the system, I mean, after you go through the homework a little bit, just so you know, I mean, if you practice enough with this, if by looking at the system it's hard for you to realize the eigenvector is 1, 1, practice a little bit more. Go back to the mechanics of how to find the eigenvectors. You should aim to do it quickly in the 2x2 case. I know that in linear algebra, if you have larger matrices, it's not that straightforward. But in the real case, the real eigenvector, it's very easy to pick. Sometimes you don't even have to write the equation, because I can tell immediately this tells me that V1 is equal to V2, right? Because if I look at the equation, V1 equals V2, so what could be the possible easiest eigenvector you can produce? That's 1, 1, right? You can plug in 1 for one of the two and get the other one, which is equal to 1 as well. So now the second step here, the generalized eigenvector. Once you're done with this, you're going to set up the same system that you see here. Write this guy, same left side, for a different eigenvector. Now call it U1 and U2, and the right hand side, the eigenvector that you just found. Notice the rows are dependent. The equation that gives you the generalized eigenvector will be minus U1 plus U2 equals 1. Lots of combinations you can find. For example, I can pick U1 to be 0 just like before, and then U2 will be 1. If you want a little variety, let's say U2 is 0, and then U1 is minus 1. So that's also can be a possibility. I'm going to choose this one just to make it different from the previous example. But any non-zero solution will do. 0 for U1, 0, 1, or minus 1, 0. And then, of course, now you finalize with the full solution, which is C1 V bar, which is 1, 1, e to the lambda t, e to the minus 2t, and then plus C2, and now the linear combination, minus 1, 0, plus V bar times t, e to the lambda t, which is again minus 2t. So again, that's going to be your U bar and your V bar, and this is V bar again. So at this point, let's actually move on with the complex case. I'm going to write a formula for the complex case on the next part. At this point, let's actually remember, or actually let's learn, because I don't think that's actually part of the linear algebra course you take for this class. Let's see how we can find the complex eigenvalues and vectors. So there is a way to do this, again, quite easily and efficiently, but you have to keep in mind of a couple of things before you move on. So again, I'm going to write down the formula for the solution on the next part of the lecture, although you can see it in front of you. But let's actually state a fact. If lambda is equal to alpha plus minus beta I, so if you have a complex eigenvalue, for a 2x2 matrix, they always come in conjugate pairs. That again, that's a fact from algebra, right? I mean, the roots of a complex, the complex roots of a polynomial with real coefficients always come in conjugate pairs, never by themselves, right? So you always have 2, 4, and so on. Now, obviously, in a second degree polynomial, like it happens here for lambda, if you have complex roots, you get 2 conjugate ones. So you get lambda 1 equals alpha plus I beta, real part, imaginary part, and the second one will be alpha minus I beta. Now, it is a fact that their corresponding eigenvectors, and by the way, the way to find the eigenvectors is really the same mechanics. The corresponding eigenvectors will have the same structure. They will be conjugate pairs. So your eigenvector for V1 will be in the form of some vector, let's call it P bar to keep up with the notation in the book, plus I Q bar, and the second eigenvector V2 will be the conjugate of the previous one. This is very important to keep in mind, because your solution, if you look at the formula for the solution, is in terms of real part, imaginary part of lambda, real part, imaginary part of the eigenvector. I mean, it's a more complicated formula, which again I won't prove. You can look at the proof in the book if you want. It's not that hard to understand, but it's not worthwhile to go over it right now. But just like in the second order linear ODE case, remember, eventually the solution is in terms of alpha and beta, real part, imaginary part. For systems, it's also in terms of real part, imaginary part of the eigenvector, but they all come in conjugate pairs. So that means if I find a pair, lambda 1 V1, you also know the other pair, lambda 2 V2. You just basically change the sign in between them. And you don't have to find it. That's the whole point, right? I mean, unlike in the distinct real case, I don't need to find 2 distinct V1 and V2, because the formula depends on the real part, imaginary part anyway. I can extract these quantities just from one eigenvalue and eigenvector pair, and then put it in the solution. But the only caveat to keep in mind is that if you choose to find the one with plus between them, you have to make sure you write your eigenvector with plus between them. So there has to be a complete agreement when you write your eigenvector and eigenvalue between the sign, with the sign between real and imaginary part. This is important because beta itself may be negative or positive. Q bar may have negative terms. So do you keep the negative terms into the Q bar, or do you put the negative term outside? That's not a trivial question, right? If you start with the lambda in that format with plus between them, you ought to put the negative terms inside Q bar, because this should be also plus. See, I mean, if you interchange the sign, it's essentially making a sign mistake on Q bar, if you don't pay attention to this. So my recommendation is, for consistency, just use the one with plus. It doesn't make it any easier or harder if you choose the other pair. So from this point on, when I find the eigenvalues and vectors for in the complex case, I'm going to just use the lambda with plus between them. I mean the version with plus between real and imaginary part. And then I'm going to just remember, when I write the eigenvector, to keep the minus, any possible minus sign, inside the imaginary part of the eigenvector. So this is important. Rewind if it's necessary until you understand what I'm talking about here, and let's proceed with the complex case on the following part, and then I'm going to focus on some other little tricks of the trade to keep in mind in the complex case as well before you write the solution. So stay tuned.